Okay, so now I have everything. Okay, so for this CAD project, what we're doing is we are taking our operational amplifiers, which we have four, and we are basically dividing 9 volts using voltage division principle into four reference voltages, and then we are feeding in another voltage, which will be compared to our reference voltage at each division level. And so, for example, let's say all of these are equal, and that means that it's going to drop the same amount over each resistor from 9 volts to ground. So the first one will be over here at the very, very top. We're feeding in 5/5 of 9 volts, or just 9 volts. Now down here we're feeding in 4/5 of 9 volts, 3/5 of 9 volts, 2/5 of 9 volts, 1/5 of 9 volts, and then 0 volts to ground, right? And so over here in this inverting input on this amplifier, we're going to be feeding in 4/5 of 9 volts. So that will be the reference for this amplifier. For this amplifier, it will be 3/5 of 9 volts. And so let's say we feed in, let's say, 3/5 of 9 volts, and it's just slightly over 3/5 of 9 volts. Because this reference voltage at the inverting input is 3/5 of 9 volts, and then we fed in slightly over that, this amplifier will turn on, and this LED, well, the output will be high and the LED will shine. Whereas this one, we're only feeding in 3/5 of 9 volts to the non-inverting input, but its inverting input, its reference voltage, is looking for 4/5 of 9 volts. And so because the non-inverting input voltage is lower than our inverting or reference voltage, this LED will be off. And so that's all we're doing. At each step, we're comparing what this V-in is to its reference voltage at each step. And so we were given these voltages down here, 8 volts at V1, V2 would be 4.3, V3 over here would be 3 volts, and then V4 we wanted 1.1 volts. With the provided voltages, we aren't evenly dividing the voltage at each step for a total of 6 intermediary steps, where we have 1 at the top, which is 9, 4 in the middle, which are divided evenly, and then which would be divided evenly, and 0 at the ground level. What we're doing instead is we know that our total resistance is equal to 20 kiloohms. That's what was provided to us, and that we are to determine how much voltage should drop at each resistor level, which is provided basically here, and then we are to determine the resistor that needs to be in place. And if we look at each step, we have 9 volts. Now we want 8 volts at this junction. So that means we want 9 volts minus 1 volt. So over resistor 1 has to drop 1 volt. And since we have 8 volts now here, for our voltage, our second voltage, we want 4.3 volts. That means we need to drop 3.7 volts over resistor 2 to get from 8 to 4.3. And then the same thing kind of continues. You can see that from 0 to V4, we want 1.1 volts. So R5 needs to be a resistor that is capable of dropping 1.1 volts. And so basically we've come up with this sort of recursive formula that will determine what the resistor value needs to be. And because we know the total voltage from 9 volts to ground, and we know the total resistance, which is 20 kiloohms, we can calculate the total current through the branch, I suppose, in a way. And that comes out to be 450 microamps. And so we can use this to compute every resistor value. And we come up with these theoretical values of 2.22K, 8.22K, 2.9K, and then 4.22K, 2.44K. So we can't get those exact values, but we can get pretty close. And so that's basically what we did to divide up our voltages in each intermediary step to get a reference voltage for each of the op amps. So we have our op amp here, and we get these two inputs for each op amp, right? We have our non-inverting input and our inverting input here. So 3 is non-inverting, that's plus. 2 is inverting, and we're putting our reference voltage on the inverting input of each op amp. And once the plus or the supplied voltage is greater than the reference voltage, the output will turn on. Now, we have 4 op amps, which is precisely what we need. We have 4 outputs, 8 inputs, and we have VCC and then VEE, or in our case, ground. So it's 9 volts to ground, is that's how we're powering this chip. And we're going to build this circuit, and we're going to be using, instead of the LM324 op amp, we're going to be using 4 LM741 op amps, because that's what this simulator provides. And we're going to build it, and hopefully we're going to see how it works and kind of get a better idea and understanding. And so let's just start with our breadboard. So I've got my breadboards laid out, and basically I'm going to try and set this up in a way that, like, this whole thing is sort of its own thing, and we're going to separate it from the V-in, which is the voltage we're going to compare it with. And so what we have is we want our op amp. So I have one op amp, okay, so I got my 4 op amps. You can see that the divots or the dimples are up, so we know that pin 1 is the topmost left pin, and we count up going counterclockwise for each. And here I have the pin configuration and functions for our op amp LM741. What we want to do is we want to provide our 9 volts on this rail and our ground on the blue rail. And so what we're going to do is we are going to just provide the power in and the ground to our op amp. So power in says pin 7, ground in our case will be pin 4 for each of these. So let's just do that. So now we have provided power to our ICs, and we want to just double check that we want V plus or VCC 9 volts on pin 7 for each of these, and we want pin 4 to be grounded on each of these, and it looks like that is correct. Now what else do we want to do? Well, if we look at the diagram, we want to split up our reference voltages and feed them into the inverting input, and that's pin 2. So I'm going to go ahead and make a voltage divider, and I'm going to use, what was this one? So we're going to be aiming for 2.2, 8.2, 2.8, and 4.2, and 2.4 kilo ohms. And so the inverting input is actually on the left side. So what I'm going to do instead is I'm gonna put down another breadboard over here, and I'm going to make my voltage division on this side, pin 2. So I'm just going to line things up. So VCC comes here. And we have 5 resistors. So VCC comes here, drops some voltage, that feeds into this pin, drops some voltage, that feeds into this pin, drops some voltage, yada yada. It goes all the way to ground. And so we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 to ground. And so VCC, this is VCC, this is ground. And I'm going to start updating these resistor values. So we're taking our voltage at each junction and we're sending it off to the inverting input on the operational amplifiers. So that'll be pin 2 for each. So this goes into pin 2 here. This goes into pin 2 here for our second. Here we're feeding our reference for our third. And then finally we're feeding our reference for our fourth op amp. Hopefully that makes sense so far. So this op amp is reaching the first voltage drop. The second one is reaching the second voltage drop, third voltage drop, fourth voltage drop. So all of them have a different voltage at their inverting input that it's using as a reference. Let's get the output, which is on pin 6. So pin 6, this. So we're going to have our LED like this. So it's worth pointing out here that I am shorting the LEDs, but I will fix that later. I'm going to use 330 ohm resistors, and these are all, so 5, 6, like that. Cool. Now ground. All of these are going to ground. Cool. So it seems pretty obvious now what's happening is we have 3 sections. We have this section all the way to our left, which is our voltage divider setup that feeds different voltages into our middle section, which is our op amp, right? And then that outputs, depending on what voltage it compares to on each level, it outputs either a high or a low, effectively, to our LEDs. And we need to connect the ground and the power. So we only actually need to connect to the ground. So I'm going to do it like this. And now everything is basically connected, except we don't have a power supply yet, but we'll get there. Finally, you can see on the document here that Vn, we're sending the same voltage to the non-inverting inputs that we want to compare to for all of these op amps. And the non-inverting input is number 3, pin 3. Okay, so pin 3, 1, 2, 3. From here, so 1, 2, 3 to here. All we need to do, feed in the voltage we want to compare to this rail right here. That's all we need to do. So now everything is basically set up. So I'm going to power everything by dropping in a power supply. I'm going to put it over here. Positive, negative, and we're done. So that's that. But what we want now is a second power supply. So this is going to power the actual circuit, and it's also going to provide the reference 9 volts that gets divided up and fed into the op amps. Now I need a second power supply. This is just going to provide the voltage that I want to compare to. I'm going to feed this into here, and its ground is just going to go nowhere for now. So this isn't really grounded, right? I'm just feeding in a positive voltage. In our circuit, the grounds are connected, but the simulation doesn't really like that. So we're just going to do it this way. Everything will work the same. Okay, I shorted the LEDs. Let us do this correctly. From this hole to this hole. Now they're not shorted. It's not pretty, but it'll work. So now, how is this going to work? As soon as I turn this power supply on, we got 9 volts feeding into all of the non-inverting inputs, right? Because our first junction should see 8 volts. 9 volts is higher than that, so all the LEDs should light up. And they do. So when we, so here is our first junction should read 9 volts right at the very top. That's fine. But it should be 8 volts here for this first op amp. So we're lowering the voltage. You can see in the voltage, we're lowering the voltage. It should be 8 volts here, 4.3 volts-ish here, and 3 volts here, and 1.1 volt here. Right? So we're going to slowly lower the voltage, and we're going to find that once we read around 8 volts, this first LED is going to shut off. Right? So we're going to lower this voltage. You'll see this green voltage sort of go down. So we're going to lower the voltage at around 8 volts. The first LED shuts off. Now we're going to do the same thing. So the second op amp is going to shut off its LED when we get around 4.3-ish volts. So we're dropping the voltage to around 4.3-ish volts. 4.4, 4.3, yeah, 4.2, right? So now this LED is off. This third op amp suggests that with the voltage drop at around 3 volts, this third LED goes off. I'm counting 1, 2, 3, 4, but it's really whatever. So right around 3 volts, and it does. And finally, this last LED at 1.1 volts. Yeah, 1.1. And that's basically, as the voltage rises, it's just basically turning on the next LED and off. Yeah, you can see that. You can see that work. So I hope that building this and explaining it and just working through it and tracking down the faults helps us all understand what's going on in the circuit, how it works, and how some of this could actually be implemented in other applications. For example, let's say this is water levels, right? These are, you get a voltage for water levels in a sump, for example. If the sump is too low, for example, passes this threshold, it'll read 4.1 volts, let's say, and then an alarm will go off when we're halfway through, an even louder alarm, or perhaps the system will shut off at 2.6. Temperature, so a thermocouple, right? So we start low, we're cooking a chicken in the chicken cooker, the oven, right? We put our thermometer into the chicken, put that in the oven. It's reading the internal temperature of the chicken, and it'll slowly rise. And once it reaches, let's say, an internal temperature of, I don't know, 70 something, 70 to 80 degrees Celsius, I'm not entirely sure. It'll, read that like 8.8 volts, for example. And instead of an LED, it'll, like the other ones, the LEDs can still be here, but on the last one, the LED also is hooked up to, I don't know, let's say a buzzer, so it'll buzz. Or maybe it sends a signal to your phone, for example, to indicate that the chicken's done cooking, right? So these are some other external applications to some circuit like this. It is effectively, in that case, an analog to digital converter, right? We're taking an analog input, the voltage, and we're basically turning it into digital outputs with states. State 1, state 2, state 3, state 4. And we can set this up with as many states as we want. We can set it up with only one state where we only have one LED. It's simply on or off, right? Anything below 2.2 volts is off. Anything above, we'll say anything below 3.1 volts is off. Anything above 3.1 volts is on, right? And so this is an analog to digital converter in that sense. So hopefully we understand what's going on. Hopefully building this circuit together kind of helps give a tactile understanding of what's going on. Anyways, thanks.